Hello guys, welcome back to my channel Gamma Di Gamma, and I'm making this video which was long overdue, but it's pretty interesting. I'm gonna feature one of my friends in this video, Yaoju Tarn. So let's get started. So let me first explain the setup we have here at hand. We have this mass m, small m, and it's like connected to the center point here with a string of length r, and this capital mass m, and it's connected with a string that has length l minus r, where l is some constant, because that's L is like how what's like the difference between these two lengths, the small r and like the length of this string for the mass capital M. So it's some L is some constant, and we have small mass M subtending an angle theta from the horizontal. You can call it the angle of depression, and it's moving this way, and a fixed support. We don't want this to move anywhere else. So first what I'm going to do is I'm going to write the position vector for the capital M. So you have well, in the x direction, well, not much, right? It's like initially it's at like 0, and then for the y, we know the length, but so if we take this as the origin, we're in the negative y direction, so we have negative of L minus r, which can be converted into, just multiply everything by a negative there. I'm now writing these as column vectors just for convenience, and the first entry of the column vector is the x component and the second entry is the y component. Fine, we can find the velocity vector the same way. Just differentiate both components with respect to time. L is a constant, so we just have a derivative of r with respect to time. I'm going to denote that as r dot. This is common physicist notation. And I would like to point out that if you want to take the magnitude of this velocity vector, it's going to be r dot squared. That's magnitude squared. It's r dot squared. Now we can find the position vector for small mass m, and that becomes negative r cosine theta. I'm just using some trigonometry here, and notice that the x component is negative r cosine theta because it's in the negative x direction, and negative r sine theta here. Now for the velocity of small mass m, we need to do a chain rule on each component, because r can also change in time as well as theta. So we have first differentiate with respect to theta. We have r sine theta, and then derivative of theta with respect to time is theta dot, minus derivative with respect to r is r dot cosine theta. Do the same thing for the bottom guy, and fine, you want to find the magnitude squared. I'll spare you the calculation. It's r squared theta dot squared plus r dot squared. Fair enough. And now we have all of these players into, we found all these players. Now let's just plug them into the Euler-Lagrange equation, which says the total kinetic energy of a system minus the total potential energy of the system is the Lagrangian, and you have to plug in the Lagrangian into Euler-Lagrange equation. This is not the Euler-Lagrange equation yet. Let me correct myself there. This is just the Lagrangian. It's a quantity, which is the total kinetic energy of the system minus the total potential energy of the system, which includes, in this case, the system includes the the small mass and the big mass. So for the total kinetic energy, half m velocity of a big mass m is, we found that out, right? The magnitude squared was this, so we just plug that in. That's just the formula of the kinetic energy plus the kinetic energy of the small mass, and we know magnitude of velocity squared is just there, r squared theta dot squared plus r dot squared. And now the potential energy of the small mass, well, we have a negative here because in the height or whatever the y coordinate was a negative. That negative, this negative will be a positive for the small mass, mgr sine theta. And then for the other mass, we have this this positive r here, and since the reference point doesn't make a difference, like we just want the difference in height basically for the potential energy. It doesn't matter whether where it was like suspended from, what total distance it is up from the ground or from the origin. We just want the difference in height. So we're basically gonna drop the L factor, and we're just gonna have negative mg times r, and that's the Lagrangian quantity I kept mentioning. Now all I need to do is plug this into the Euler-Lagrange equation. Now the Euler-Lagrange equation is as follows: partial derivative of the Lagrangian, the quantity we just found out, with respect to so for this we can choose any free variable. So q, just I'm writing it generally first, is equal to time derivative of the partial derivative of the Lagrangian with respect to the q dot whatever free variable. So in our system we have two free variables, because if you look at this differentiation, we could only do them with respect to independent variables. So the two independent variables in our system are r, this r, and this theta here. So we need to, for q, we need to do two cases. So case one is when we have r, and case two is when we have theta. So let's do case one when we have r. I'm just going to substitute r dot here, and then I don't know, just you have the Lagrangian, just do the math, plug everything in. Mr theta dot squared plus mg sine theta minus capital M times g is equal to the time derivative of this quantity here, m times r dot plus small m times r dot, which can be rewritten as m plus small m times r double dot. Fine, that's one raw equation we have. And fine, let's do it for the theta case. Just plugging theta into Euler-Lagrange equation. Do the math. Mgr cosine theta is equal to the time derivative of mr squared theta dot, which is going to become 2mr r dot theta dot plus, this is using product rule now, m r squared theta double dot. Fine, we have the second crude equation. Now if we define small k to be small m divided by capital M, which is some constant, some proportion constant or whatever, we have basically two important equations. So r double dot, acceleration, the linear acceleration, if you want to think about it that way, is k times r theta dot squared plus g times sine theta minus g divided by L plus k. That is equation number 1. Theta double dot is g cosine theta minus 2r dot theta dot divided by r. That's equation number 2. You get these by basically rearranging these crude equations we had here, and I'll call this A, call this B, rearranging these crude equations here. And notice these are like coupled equations, because like R is also in the theta double dot equation, and theta is also in the R double dot equation. It's like a coupled ODE problem, which is pretty hard to solve. It's not trivial. Let me break that to you. And it's also not linear in R and theta, because if you, I mean, you can check that out. And as a consequence of that, we can't even do the eigenvalue eigenvector analysis that we could have done for that we actually did for the three spring 2 block oscillator system. I mean, there's I can send a link to that video, just check that out if you haven't. It's a pretty cool video. We can't even do that. I mean, this sine of theta is not just theta out hanging out there, same thing with this guy here. So it's not linear in R and theta. So ditch eigenvalue eigenvector analysis. We need to, we can't really solve it. I mean, there's ways of making computers solve it. I'm not going to get into the details of that, but we can I don't know, try to predict some values by plugging in some things and doing some basic computation on it using Python or whatever. So I thought, I mean, in a traditional video on my channel we would have ended here saying this is some complicated shit that we can't do right now. But this time my friend Yaoju Tarn, he's from Singapore, but he has lots of experience with modeling this stuff or running codes about this stuff. So he's gonna explain what he's gonna do with Python, how he's gonna plug everything in a Jupyter notebook. He's crazy. He's a genius in mechanics. So I thought it would be great if he made a video on my channel. So yeah, I'm gonna hand it over to him now.
Hello everybody. Today we'll be going through some code to compute the critical point at which the big mass starts to rise, because initially it falls, but then at some point it actually rises back up, and you can see plenty of these videos online. So let's get started. This is Python, and obviously import numpy as np. Everybody knows that. Now we set our initial value of r. I'm gonna say it's 1, and our initial value of r dot, which I'm gonna say is 0. And we just initialize everything else. So theta, that's 0, and theta dot starts from rest. Again, it's 0. Now I'm gonna define this little infinitesimal time dt. I'm gonna say it's 0. Let's just put a bunch of zeros, don't care, it's just something small. And g, the acceleration due to gravity, I'm gonna call it 9.81 instead of 10, because why not? And in our equations of motion we had a parameter k. It's dimensionless. It was defined as m over m, like that. Let's just say I want to set it at 1 over 2. Alright, and now we also have to define a counter, because we're going to use a for loop or a while loop. So what is this condition? While r dot is less than or equal to 0. That's because r dot is the velocity of the string, and it's going to be negative and increasing up to a critical point where it's positive. So this is our condition, and we want that final time as well as probably the final angle. So while this, we got I plus equals 1. That just sets the counter in motion, and we define r 2 dots equals to, from our equations from earlier, we have k times r times theta dot times theta dot power 2 plus k times g times pi dot sine theta minus g, and the whole thing over 1 plus k. So that's defining our R2 dots, our double dot. Now we define our theta double dot as from our equations from earlier. We have minus 2 times r dot times theta dot plus g times of cosine of theta over r. And now how do we introduce that dt? How do we make this dynamic? We say r equals to r plus r dot times the dt, and r dot equals to r dot plus r2 dots times dt. So now this encodes how r changes as well as how r dot changes. And we can do the same for theta. So theta is theta plus theta dot times dt, and theta dot equals theta dot plus theta 2 dots times dt, like so. And we should be done. So now we just want to print, let's say the final time is, and we can string it with I times of dt, which would give us how many time steps have passed, how many times this loop has run, times the dt, which gives us how much time has passed. So, and we also want the final value of r is, and we string that with just the value of r. And finally we print, we want to know the angle theta has gone through. So that would be the string goes through an angle of theta. And now we let it run. It's taking some time. Maybe I shouldn't have made the time step so small. Oh well, let's restart the kernel. This was probably a mistake. Let's try it again. Okay, so now we have some values for our critical time, the r when the big M starts to rise, and the angle the string has gone through when this happens. And now we can just play around. So let's say this is when the big M was twice the mass of the small m, what happens if it's 10 times? Let's run it again.